What are the best? Right. Yeah, I got that. Like all those three mount and such. Yeah, I was just, it was the same thing. I was writing fast. Right. Oh yeah, like
okay, let's get started. So today, as I have promised you last time, the first thing I'm gonna do is to go over solution to homework 1 briefly, so that you can kind of check against yourself if you have done it. If you haven't done it, then this is a good opportunity for you to try to catch up and understand what's going on. So homework 1 has 2 problems. The first one is relational algebra. The second one is a simple test on your understanding of relational model. Relational algebra, the first one, the first few are pretty straightforward, right? I think let me go with D, right? Let me go with D. Because the first 3 are quite straightforward, and you should be able to figure them out fairly easily. Let's look at D. For each dealership, find all car models sold at this dealership that are liked by none of the customer who visit that dealership. So this is a really bad dealership, right? You choose to run all the models that none of the customer ever come to that dealership actually like. So what's your point, right? But let's say we want to find all such dealerships. So how do we do it? Well, the basic idea is you find out from the visits which customer has visited which dealership. And you can find all such pairs by projecting out the customer name and dealer name from the visits table. Okay? Then you join that with likes. And then you project out the customer and model. What does it give you? What does it give you? You put out the dealership model. What does it give you? Can someone tell me? What does it give you?
It gives all the models that are liked by customers who visit a dealership.
Okay, Charlie is right. Let me try to rephrase what he has just said. You put out a list of dealer name and model such that, first of all, this model is liked by at least one customer who has visited that dealer. Okay? You put out the model that this dealer has served that at least liked by one of the customers. You don't have to be liked by all the customers who visited that dealership. At least one of the customers who has visited that dealership and liked that particular model. I want to find all such combinations, the dealer name and the model, such that the model is liked by at least one of the customers who has actually visited that dealer. And that's the combination I'm getting here. Then if I use the combination of dealer name and the model from the serve table minus away this dealer and models that I just get, what do I get? I essentially get this minus, right? What do I get? I get the model served by the dealer liked by none of the customers who has visited the dealership, which is what the question had asked for. Okay? So that's D. Look at the next one. If you have any questions, stop me anytime, right? We can discuss this further. But all customers who visit only those dealerships that serve some car models they like. Okay. So what it's asking here is you need to find the customer who visits at least some dealership that serves some car he or she likes. But that's not good enough. Because among these customers, they may visit additional dealership that serve none of the cars he or she likes. So if you're able to find these two sets and do a set difference of the two, you get the customer who visit only those dealerships serve some car he or she likes. You follow my argument? Okay? That's what the solution is trying to do. Okay? Look at E, right? So this part join, the natural join between likes and serves and put out the customer name and dealer name, give you all the possible combinations between customer and dealers such that this customer visits a dealer that serves at least one car he or she likes. But be careful, here it doesn't tell you that customer has actually visited that dealer. It only tells you if you do visit that dealer, that is a dealer has at least one car that you like. But doesn't mean you have actually visited that. I just want to find all such possible combinations. You follow me? This part. Okay? That gives me all the possible combinations between customer and dealer such that if this customer do visit that dealer, I'm sure that dealer has at least one model that this customer will like. Okay? Then I use the projection of customer and dealers from the visits minus weighted ones. What does it give you? What does this part give me? What does this part give me? Hello? What's your name? I think I've asked about that before.
Mission.
Huh?
Mission.
Say again?
Mission.
Okay. What does this give you? This part. We're gonna time it. Okay, 3, 2, 1. Time is up. What about the person sitting next to you? What's your name? Identify yourself. Huh? Zhao. Tao. Okay.
The customer name and the dealer name that the customer has visited, so
No.
I don't know all
The customer has visited a dealer for
Yeah.
sure.
and that does not like.
Does not like that dealer. Well, there's no like relationship between customer and dealer, right? Customer only like cars. We are not trying to capture which customer like which dealer, right? Well, but you are almost there. So what this gives us, if you only look at this, that for sure gives us what you said in the first part, which is customer visited that dealer. But minus away those customer and dealer combination, where the customer like at least one model served by that dealer, that gives us the customer who has visited a dealer, but he or she likes none of the cars served by that dealer. You follow me? And that's the key to solve this problem. Because after this step, I can print out the customer name. That gives me the list of customers who have visited some dealer, at least one dealer. At least one, maybe more, but at least one dealer that serves none of the cars he or she likes. You have visited at least one such dealer. And that's the set of customers we're getting from here. Then if I use all the customers from visits, by the way, you have to use visit here. You cannot print out the customer from the customer list. The reason for that, I will ask one of you to tell me why that's the case. You have to use visits in order to do this projection of customer name. Minus with these customers, that gives us what? That gives us the set of customers who only visit those dealers that serve at least one car he or she likes. So let me throw that question out. What happens if I change visits to customers here? Would that change the semantic of this query?
So if you had a customer that hadn't visited anywhere, they would have a different use case.
That's absolutely right. What's your name?
Eric?
Eric. What Eric said is if I do change this from visits to customers, I get all these customers plus those customers who have visited nowhere yet. Okay?
So on E, when you say visits minus the cross product of likes and serves, so it looks like,
You mean this one?
no, to the right.
This one?
Yeah, so it looks, can that be replaced with division?
If I replace that with the division, okay.
Well, and then modify the projection for the cross product.
You mean the next job? This is not cross product, right?
Oh yeah, sorry, the joint.
And what do you want to modify that to? Project only the customer name or dealer name?
The dealer name?
Project only the dealer name.
Yeah.
Okay, let me write it down. So Daniel says, if I modify the query like this, what happens? Oh, sorry, dealer name. You said, right? Is that what you said?
Yeah.
Okay, let's look at this together. First of all, this stays the same. It gives you the natural join between likes and serves, basically all the possible combinations between who like which car and which car is served by which dealership. It doesn't mean you have actually visited a dealership, it just says these are the potential combinations between customer liking a car and this car happens to be served at one particular dealership. I want to find all such combinations. And that's essentially what this natural join gave you. Do you follow me? Customer like car, car served by a dealer. That's essentially captured by this. And then I put out these dealer names. What do you get? You essentially get all the dealership names except those dealers serve cars liked by no customers. However, this is different from serve cars not liked by anyone who have visited a dealership. These are two different things. And do you follow me? What you get here is the dealers who serve cars that no customer, whether that customer has visited you or not, like by no customer whatsoever in my database. And then you figure out these ones with it, and divide by that, what do you get? You get the customer visits all dealers who serve cars liked by no one. You have visited all such dealerships.
But wouldn't it be like
But let me finish this before Charlie comments on this. And that is different from what the query asked me. Do you follow me? Because there's a subtle difference. Because what the query was asking is, find the customer who visit only those dealerships that that serve some car he or she likes. What we are trying to find here is, you have found the customers who has visited at least one dealer serve no car he or she likes. But that's different from serve cars not liked by anyone. That's the key difference. Okay?
Isn't
Charlie.
it just a reciprocal, what you said, like the projection on the right side of that division is just, it's the set of all dealers who serve at least one car that's liked by at least one customer. Because it seems like...
Yes, that's right. That's right.
Okay.
This is the set of dealerships that serve at least one car that liked by at least some customers.
Yeah.
Maybe just one, I don't care, but at least you serve one car that liked by someone. Then you will be here. What's not here, what I'm saying, if you compare this, if I call this the set T, if you compare this against there is a table called dealership, right? If you compare this against T, if I use this minus T, what do I get?
Yeah.
That's essentially the dealers that serve cars that nobody likes. Okay? So this gives you the customer who has visited all the dealerships that serve at least one car liked by someone. You follow me? But this is different from what this particular query is asking for. Okay? Alright? So relational algebra might not be as simple as you saw. Right? I mean, it's 5 basic operators, but the combination of this can be really tricky if you want to get it right. Let's look at the next one. This F is very similar to E. It says find all customers who have visited every dealership that sells some car model they like. And this is a very practical query, right? If you are on the market of shopping for a new car, you probably will do something like this. You visit all the dealerships nearby you that sell some car model you like. You compare, you test drive, and then you make your final decision. So if you do some kind of marketing research, you might want to find all those customers who have done just that. That's essentially what's going on here, right? So how do you solve this problem? Well, this is different from E in the sense that E says you find the customer who visit only those dealerships that serve some car they like. But there's a subtle thing over there. You visit only those doesn't mean you have visited all of them. It only says you don't visit other dealerships that serve no car you like. For the dealership that do serve some car you like, you don't have to visit all of them. You just need to visit some of them. As long as you haven't visited any dealership outside that range, then you're fine. You will be qualified as a customer for E. But for F, it says you need to visit all such dealerships that serve some car you like. I don't really care whether you have visited some additional dealership that actually serve no car you like. You can do that. But given the condition that you have visited every dealership that has some car you like, then outside that, I don't really care. That's what F says. You follow me? So how do you do that? So if I draw a set, I think it's easier to do this. Customer witness D, a dealership that has a car A-shaped lights. Okay, that's one sentence. Okay, you follow me? That's one sentence. And customer visits okay. Okay? Do you follow me? So this is F. F is asking for this. And what is E? E is asking this minus this. That's the difference between E and F. Okay, that's the difference between E and F. Obviously, this is a subset of this. Sorry. Why? Because if you have visited every dealership that sells a car you like, then obviously you have visited a dealership that sells a car you like. You follow me? But F may also contain some customer from here, because as long as you have visited every dealership that sells some car you like, I don't really care what you have done with other dealerships. So this, the keyword every dealership, that's a strong indicator for using the division operator. That's a very strong indicator for using the division operator. Right? So for, basically you use visits, divide by the combination between customer and dealership, that dealership sells some car he or she likes. That will potentially give you the customer who has visited all such dealerships. And that's essentially, I believe that's essentially what has been done in this particular solution. Actually not, it does not use division. So let's look at this together. So you use slides, natural general reserves, and put out, actually, yeah, I remember this. This is a very good one. All it does is to flip the order of these two terms from E. Then you get the solution for F. I will ask one of you to explain to me why that's the case. Why I simply swap the order. And that will give me the solution to F. Yeah. So that's a good start.
We need to find our dealer which serves all the models customer like minus all the dealer this customer has.
Then, okay. Anyone try to help? How about you? What's your name?
Anita.
Yes. Okay. Right. Can you give a try?
You get the first part will give you customer if there is any the list of all customers and dealer dealer name where you at least serve any of the cars you like.
Okay.
And then you find the subscriptions of the customer name and dealer name. So those customers who didn't visit any of them, that will be gone.
The customer didn't visit any of them.
That will be gone.
But this particular claim is wrong. It's not didn't visit any of them. So what you said, this part is right, but this is essentially what I said earlier. That gives you the combination of customer and dealers that customer like at least one model sold by that dealer. You minus away the visits, the combination between customer and dealers from visits. What do you get? You get the combination of customer name and dealer name such that the customer like at least one car sold by that dealership, but he or she hasn't visited that dealer yet. That's essentially the combination you get from here. Then you put out those customers. What is this list of customers? This list gives you all customers who haven't visited at least one dealership that serve at least one car he or she likes. But if you are a customer from this list, that's precisely the customer I want to get rid of. Because by the requirement of this problem, you need to visit all dealers that serve at least one car you like. If you haven't visited at least one dealership that serves a car you like, you are disqualified. Then the final step is simple. I simply use, again, for this very same reason that Eric had argued for, we do need to use the customer from visits instead of customer from the customer table for a very similar reason. Then minus away this set of customers, you get the customer who has visited every dealership sold a car he or she likes. Okay? What about next one? Next one I think is,
Excuse me.
yeah, go ahead.
So why not use the division?
I believe this one you can use division operator too, but we can do that approach offline if you're interested. Okay. Find those customers who enjoy exactly the same set of cars as Mike does. This one is essentially a division. You find all the cars Mike likes, then you do a division. I think that's fairly straightforward. So I will skip this. One thing I could ask you, which is I think is not in the homework, which is go beyond F. I can ask you, find the customer who visits every dealership that serves some car he or she likes, and only those dealerships. You see that? That's essentially asking you to do this set minus this set. And how you do that, right? I will leave that as an exercise for you to figure out. Okay. All right, now let's continue to H. For each car model, find the dealers that serve that particular car model at the lowest price. This is a challenging problem to solve in relational algebra. Fundamentally because we do not have aggregation operator in relational algebra, meaning that we do not have things like mean price, right? You cannot find the minimal price for a particular car model. Then if that's available to you, then this problem is not that hard. For each car model, you find the minimum price, then you naturally draw that, the combination between car model and the minimum price of it, naturally drawn with the served table, you get the dealer that served that car at exactly that price. And then you're done. Right? But we do not have aggregation operator in relational algebra. How do you go about solving this particular question? Well, the trick is to do a self-join. You do a self-join between served. You make two copies of the served instance 1, instance 2. Make sure the model match, but price is different. That means you find a dealer that serves the same model at a different price. That only tells you they serve this same car model at a different price. It doesn't tell you it's the lowest one. You follow me? But if you make your condition of greater than, rather than greater than or equal to, and equal to, then you find all the dealers that serve this car model at a price higher than some other dealership. Not necessarily that all the dealership, but your price for this model is higher than one of other dealerships. But if you happen to be the dealership that serve this car at the lowest price, you will not be in the joint output. That means, automatically means you are the one serving this model at the lowest price. And that's essentially the solution. Okay? So you do a self-join. So you use the renaming operator to produce two instances, two copies of the same instance, of the served instance. Then you make sure the model are the same from these two instances when you do a self-join between them. But the price from the first instance is greater than the price from the second instance. Then you purge out the combination of dealer name and model. What this gives you is the combination of dealer names, and car models such that this dealership serves this car model at a price higher than at least one other dealership. So the critical observation is the dealership that does serve this model at the lowest price will not be in this output. Then you use all the combination from the served minus with these guys. That essentially precisely gives you the combination of dealer and model at the lowest price. Okay? So again, if you are on the market for shopping a new car, you can ignore all the other solutions, but you do want to remember this one to find the model you like at the lowest price. The next one, the next two are degree operators. I think they're fairly straightforward, so I can skip that. Okay. Any questions on this? Yes.
So on that last one, if one dealership serves the same model at a higher price, like if it has one model but at two different prices, would that still work?
One model at two different prices. First of all, by our schema, that case will not happen because the primary key for the serve is dealership and model, not with the inclusion of price, which means the combination of dealer and model can appear only once. So if this model appear at that dealer, it should appear only once. Okay. That said, if we change this to the schema to dealer name, model, and price, meaning that we cater for the case where you serve the same model but at different price. You may wonder why that could be the case. Well, I may serve new car and old car, used cars of the same model, right? Then of course you're gonna have different prices. If that's the case, then this particular solution will not work. But what you can do, I think, in that case, you can put that out not only the dealer name, model, but you can put that out also the price of the higher price. Then you serve minus that. That will give you the dealer and model and the price. That give you the lowest price for that model, even if the same model is sold multiple times in a given dealership. Okay. And you have something to add on?
Yeah, can you show the answer for F again?
For F,
Yeah.
for this one, find all customers who have visited any dealership to serve some car. Okay, sure. Okay, so what we are trying to do is, so instead of showing a solution, I will just do this calculation on the chalkboard from scratch, okay, all right? So that you can follow me, rather than looking at the whole solution. So you want to find the customer who has visited every dealership that serves some car he or she likes. So how do you go about doing this? The first step is to find the combination between customer and dealers such that this customer likes a car served by this particular dealer. You find all such combinations, and that's easy. You just do likes, that you want, it serves, then you put that out. Okay? And the natural join will happen on the model based on our schema. Okay, you join on the model. This is all the combination between customer and dealer name such that this dealer serves at least one car he or she likes. You follow me? Then you put that out from visits. Customer name and dealer name from visits. What do you get? You get all the customer who had visited that dealership. The combination of customer and the dealer. That customer had visited the dealership in concern. Then you subtract this set from the first one you just got. What do you get? What does this whole thing give you? This gives you the combination between customer name and dealer name that dealer served a car he or she likes, but that customer hasn't visited that dealer yet. And these are precisely the set of disqualified customer with respect to this query. Because to qualify for this query, you need to visit every dealer that serves a car you like. If you haven't visited at least one dealer that serves a car you like, then you are disqualified. So that's why we simply put out all the customer from this. These are the DQ customers. The DQ customers, the disqualified customers. Then I use, the final step is almost straightforward. You find all the customers who actually have visited some dealership, minus away those customers who has not visited at least one dealership, serve a car he or she likes. That gives you the customer who must have visited every dealership he or she likes, serve a car he or she likes. Yeah.
So one reason I was confused on this problem is because we mentioned that division is useful for all queries. So when I saw the word every, I kind of thought to myself that a division might be involved.
Okay. So yeah, that kind of goes back to what he was asking earlier, right? Can we do this using division? I haven't solved this using division myself. I haven't attempted to do that yet. I'm not going to do that now because it may take some time. I will try to think about that offline. But my gut feeling is this one, visit every dealership. Let's think about it. My gut feeling is this will be difficult to do using division, if not impossible. The reason is you are looking at the combination of dealer and customer. So if you think about A divided by B, right, well, the critical thing is to figure out what's B. What is B, right? It looks like for a given customer, you can do this fairly straightforward. For a given customer. But if you're looking at all the combinations of customer and dealers, then this becomes hard because whatever you put into B, it will be too much to divide by.
Maybe you could do like a self-join with, like, so you could add basically, like, duplicate the customer name.
But the challenge is, again, in the B, because the division semantics says for every tuple in B, you need to find a matching pair in A. So it's tricky in this particular case, what goes in B?
Could you do like likes in natural join with serves?
Like natural, yeah,
Basically.
I was thinking about that.
Yeah.
So you just get this.
Yeah.
But the thing is, this is not for one customer, it's for multiple customers.
Right.
So there will be combinations of customer and dealer name that are not in your A, but still fun, because I don't have to care about other customers. For a given customer, I only care about myself.
Right.
Like the dealership that serve a car that I like.
Right.
But if you put all the customer and dealer combinations into B, then you disqualify essentially every customer. because I cannot be responsible for what other customer likes. That makes sense?
What if we had for A, like, just, okay, maybe I should include that, but what if we had for A, just like,
Well, what you get if you use this as B, what potentially you get is a customer who has visited all dealerships that serve some car liked by some customers. Because you're getting all the combinations of customer and dealers, right? So it's I do not want to exclude the possibility of doing this using NVIDIA, but by just looking at this, I think it will be extremely hard, if not impossible, to do this using NVIDIA. With that said, I would like to take this offline. Let me think about it offline and get back to you guys, maybe at the beginning of next lecture, to give you a definite answer whether we can do this using NVIDIA or not. My gut feeling looks like this will be unlikely. Okay. All right, that's all. I think problem 2 basically is a test on your understanding of the basics for the relational model, which is essentially the key, the concept key, right? So it's just a quick recap. I'm not going over this particular problem, but just give you a quick recap of what's key. So these are the things we talk about. These are the concepts associated with key, right? First of all, you have key, you have super key, you have primary key, you have candidate key, you have foreign key. First thing first, if you draw a diagram like this, that's all your super key. And key essentially is a subset of super key. And among all the keys you have, you choose one of them as your primary key. And the rest of them, except this dot, this one guy you have chosen as your primary key, become your candidate key. And what about foreign key? Foreign key is one of these from the set of keys taken out from this table and placed into another table. Then on the second table, it becomes a foreign key.
Does the foreign key have to point to the primary key, or can it point to any?
It can point to any key, not necessarily the primary key. But it has to be a key, not a super key. Good question. Okay. So that's essentially what is being tested here. So one thing you can, another observation you have is, given any key, whether it's a primary key or candidate key, given any key, you can always produce multiple super keys by attaching additional attributes to that key. Of course, from the same schema. And that will give you additional super keys for that given schema. That's essentially what this question is about. And with that said, I think I'm done with reviewing the solution for homework 1. And I will release solution to homework 2 on Thursday, which is 2 days from now. So if you haven't started solving those SQL queries, you should get started. You don't have to, I don't expect you to solve all the SQL queries over there. There were about 26 of them. You don't have to solve all of them. You solve, let's see, if you can solve half of them, then it's a pretty good progress, if you ask me. Please. Yeah.
So but it says, oh, never mind.
Yeah.
The website just has, it says due Monday, 9/23/13.
Yeah. Okay. Anyways, now it's due Thursday. Okay. Oh, it says due on Monday.
Yeah, it says due Monday.
I think I made a mistake on the due date.
2 years ago.
Okay.
I have still one doubt in problem 1G.
Okay.
So when we make the division, then we get all the car models which Mike likes, plus other models also the other person.
So you need to minus away those customers who like.
You get that minus.
For the mic, this one, right? So you get this part, right? That's fairly straightforward, right? So the trick is actually similar to the customer dealership example, right? The customer liked a car that's sold by a dealership. The trick is you find all the models that Mike liked, find all the customer name, cross product of them. That gives you the combination between customer and models that are liked by Mike. Then you use likes minus with this, what do you get? You got the combination of customer and model such that the model is not something that Mike likes, but liked by a particular customer. And you put out those customers. Those are the customers like at least one car that Mike doesn't like. and then you use all the customers who like all the cars that Mike likes, minus with those customers, that give you the customer who like exactly the same set of model as Mike does. Does that answer your question? Okay, very good. So I think now we finish reviewing all these solutions here. So I will do a similar review for SQL later on once I release the solution to SQL. And then we are ready for doing a quiz on relational algebra and SQL. Okay. All right. With that being said, I think we should definitely go on to our lecture. I have released, by the way, project number 1. I'm hoping that I can finish the discussion on the disk space manager today. That covers what you need to know about project 1. And project 1 is due 1.5 weeks away from today. So let's get started. So we talk about, am I looking at the wrong one? Sorry, looking at the wrong slide. So we talked about the structure of disk, and that's where we stopped last lecture. So I'm going to do a quick review of that, and we'll move on. So regarding this, there are basically 3 types of costs that you need to remember. One is the seek time delay, which is moving the ARM assembly in and out to align the head to the right track where your page locates at. Then there's the rotation delay, meaning that once you have aligned the head of your ARM to the right track, you still have to wait for the starting sector, the first sector in your page, to be rotated just right below the head of your ARM. That's the rotation delay, which typically is calculated by the average of 1 rotation, the time that takes, the half of the time that takes you to do 1 rotation. And then finally there's the transfer time cost, which is once you have aligned the first sector to be right below the head of your ARM, you have to convert, you have to do the converting, and that costs you time as well. And this transfer time deserves a little bit more discussion. When you do that transfer, there are 2 things involved. One is the converter itself, which is to convert magnetic field into electron signals. Then there's another thing, which is at the same time, you still have to keep doing the rotation. You have to keep doing the rotation. Because if you think about it, suppose this is the page that you're looking for. Your ARM head is here. Okay? You start reading data, you start converting data. Not only you need to convert that, you need to wait for these guys, all of this sector to be rotated under you, and that takes time too. So the transfer time comes from these 2 particular components. One is the converter itself, the other is the rotation. How long does it take to rotate this many data to be go through the head of your ARM? So how do you calculate this part? How long does it take to rotate it? Well, you use this divided by the time to, the amount of data available in one track, and times that with the time to do 1 rotation. That'll give you the proportion time that you need to rotate this many data over your head.
So solid state drives eventually become cheap enough. Would it make sense to replace hard drive disks and databases?
So that's the next thing I'm gonna talk about. So now we understand hard drive. Okay, I think I talked about enough about hard drive. So let me go on to some other storage media that we briefly mentioned. We mentioned cache, we mentioned memory, we mentioned hard drive, we also mentioned solid state drive, and tapes. I'm not gonna talk about tapes. but I do gonna talk about briefly solid state drive and memory and their relationship with hard drive. This is kind of in response to Daniel's question as well. So first of all, solid state drive. So as we can tell from the discussion on hard drive, obviously when you access data from hard drive, from hard disk, there's a huge difference between random access and sequential access. Okay? Because you have to do this arm movement all the time for random access, and for sequential access, this cost is amortized over the many pages you're gonna access. You do this at the beginning for the first page, then you cannot stay put. Just wait for the second page. So sequential access is much more efficient than random access when you go accessing data from hard drive. What about solid state drive? Well, a critical feature of solid state drive that makes it so popular, like a lot of laptops nowadays use solid state drive, is that for read-intensive workloads, solid state drive is extremely efficient. In particular, the solid state drive makes no difference, almost no difference in random access or sequential access. So if you do a random access on solid state drive, it gives you pretty much the same, almost the same speed as if you are doing sequential access on solid state drive. So that's a big plus compared to hard drive. That's reason number one. Reason number two, reading data from solid state drive is much faster than reading data from hard drive. And that makes it really attractive as well. Yeah. But there's no free lunch. And what's the downside? The downside of solid state drive is the expensiveness associated with write. In particular, update. Update means that it's not an insertion of new data, rather you are trying to update some existing data that are already on your drive, on your solid state drive. Why updates are so expensive? Because in solid state drive there's a there's something called reader block. And the basic idea is if you try to suppose this is a block. So for now you can think of this as a page, but in practice a solid state drive, the e-reader block is often bigger than a single page. It's a collection of pages. Okay? It's a collection of pages. Like typically this is in 64 kilobytes or 128 kilobytes. If you have 4 kilobytes page size, this is roughly 16 or 32 pages that are organized into a block. And that's what we call the e-reader block. What happens in solid state drive is update to a particular page. You can imagine for now, just for simplicity, imagine this is a single page. This is a single page. To change any bit on a given block, if there are already data in it, you cannot simply do in-place update. What you have to do, if it's a solid state drive, is to copy this out, this whole block out to to a particular location. Copy them out to a particular location, update them, and write them back. That's why it's called e-reader block. You have to copy them out, erase this, update, then write it back. So this is really expensive, as you can tell, right? Not only that, the particular property, the physics behind solid state drive, makes this e-reader not only expensive, but it reduces the lifetime of the drive itself. It dramatically reduces the lifetime of the drive itself. So if you do a lot of random updates on a solid state drive, the lifetime of your drive will be reduced dramatically. Okay? So make it really expensive in practice as well, meaning that over time, if you take time into consideration as well, over time you're gonna spend more dollars for storing the same number of bytes if you do a lot of updates over those bytes. Do you follow me? So that's the problem with SSD. So in practice, but it does give you memory-like behavior because we talk about RAM, random access memory. Random access and sequential access make no difference, and that's pretty much the property that solid-state drive gave you. In addition, it's much faster than accessing data from hard drive, which is really attractive as well. And at the same time, it's non-volatile. It is non-volatile in contrast to memory, which is volatile, which means if you lose power, your data gonna still be there. So solid-state drive is really nice, but when it comes to updates, solid-state drive becomes super expensive. Okay, becomes super expensive. That's why for if you think about the kind of workload that you do daily on your laptop, if you think about one thing I want to emphasize. If it's a write of new data to a block that has no data currently sitting in that block, then this is cheap. This is not expensive in solid-state drive. You can just directly write to that block without doing this expensive reading operation. You follow me? So pretty much if you're doing a pen-only operation, that means you write to the solid-state drive sequentially. New data coming in from time to time, either continuously or from time to time. This is okay. This is actually not that bad, both from speed-wise and from the impact to the lifetime of the drive. From both aspects, this is not too bad. You just write to it sequentially. However, once you try to go back and do random updates, that's when it becomes really expensive. If you think about it, this makes it good for things like laptop, right? If you think about the workload you do on your laptop, oftentimes it's about saving a new file, okay, and browsing and reading data for the most part, and occasionally you do some update to some existing files. But it's not too intensive, right? It's not like you're doing random updates to your laptop all the time. I mean, that would be really rare, if you ask me.
What's the average lifespan of an SSD?
Well, that's a really hard question to answer because that depends on your usage pattern, as I just explained. Because if you do a lot of random updates, then the same drive will die fairly quickly. But if you don't do random updates, you just do append only and read only, then it will go pretty long.
And an update operation on this would still, even though it's expensive, would be less expensive than an update operation on a hard drive.
Well, if you do random updates, of course, the numbers, the absolute value, like the time, how fast it can be updated, depends on the manufacturer. Right? But generally speaking, if you do random updates on SSD, it's not going to be much faster than writes to a hard drive. So it's drag it down to milliseconds level for random updates. For append-only updates, it's still very fast. It's almost as fast as read from solid-state drive.
Could you repeat that?
For append-only operation. This is also right, but it's like writing to a new block continuously. This is pretty fast. This is almost as fast as reading data from solid-state drive, which is much faster than reading data and writing to hard drive. So it really depends on what kind of operation you're looking at, and also depends on the particular flash drive you're using. Because there are two popular technologies go into flash drive as well. There's NAND, and there's another one I forgot. There are two different technologies that people use to build solid-state drive as well. Okay, so what happens now is typically in a data management system, what people do is to use solid-state drive as an additional buffer to your hard drive. What that means? That means you cache frequently access data on your solid-state drive. You cache them on solid-state drive so that reading data from those will be much faster than reading data from hard drive, and you can be careless about random access and sequential access now. In contrast, when you do with hard drive, you need to be really careful in random access and sequential access. So that's point number one. Point number two is you use a particular structure called log structure index of file. Log structure index of log structure file. What is that? I will talk about this when we finish talking about the typical classical file structure in a database system. Then at the end of that discussion, I will come back to this. Just remember this. There's something called log structure index, a log structure file. That is very popular, the primary structure to organize data on a solid-state drive. And the reason for that is it has to do with the particular property of solid-state drive that we have just gone over. Okay, so that's the discussion on solid-state drive. What about main memory? Main memory is very nice. It doesn't have this problem that solid-state drive has, meaning that if you do random updates, it can still be very fast. It makes almost no difference between random updates and append-only updates. However, the downside is, besides price, of course, price is always a factor, but besides that, if you don't care about how much money is thrown into this storage medium, one critical thing, downside about memory is it's volatile. It means if you lose power, your data is gone, right? So you do need at least a solid-state drive or a hard drive that can back up your data permanently in case of failure, right? But the picture is changing, right? There is something called NVRAM. NVRAM. You can Google this, but basically it stands for non-volatile RAM. NVRAM, non-volatile RAM. That means it's a RAM, but it's non-volatile. So it's like really a nice thing to have, right? Because it combines the benefit between memory and disk. But of course, the price of this is going to be expensive, right, as you can imagine. And it's not commercially available yet. There's no product now you can buy. It probably will be available a year from now, I guess, a year or two from now, by Intel and Micron at Boise. They are building this. There are some prototype available, but what we can get outside the company is some simulator they provide that you can test and design your program on, but they do not have physical device available yet, physical NVRAM available yet. But this will be something really interesting to watch out. Okay, really interesting to watch out. Still, even without NVRAM, increasingly, like Daniel has pointed out, memory size become bigger and bigger, and people are increasingly interested at building main memory data management system and using hard drive as kind of like a backup device to cater for the rare case when something goes wrong. You can get your data back from hard drive. But as I argued in last lecture, if you want to host really large amount of data, a single machine memory space is not going to be enough. Not going to be enough. You have to use a cluster of machines to do that. And there were projects like that, like RamCloud, we briefly mentioned that. However, all of this, if you look at all of this memory data management system, they still have to, for a very large degree, they still have to worry about a persistent storage, which oftentimes is a disk. They have to worry about the interaction between memory and hard drive for backup, for accessing quote-unquote code data, and so on and so forth, right? So it is still very important for us to understand the role of hard drive and how that plays in a relational database management system. Of course, that said, toward the end of the semester, when we have time, we will talk about the main memory data management system as well. When we wrap up the discussion on classical design of relational database management system. Okay? All right. So that said, let's move on. Talk about all of this. So next, let's look at buffer management. So now we understand hard drive, which hosts your data on disk. The next thing in hierarchy is something called buffer, which is essentially a collection of pages in your main memory. A collection of pages in your main memory. And it's organized into this conceptual, you can imagine this as a conceptual rectangular box in your memory, right? Where each small rectangular box each of this denote a single frame. A single frame, a frame is a size of a page. A frame is the size of a page that is going to hold a page of data that you load from disk. Whenever you load the data from disk, it has to go somewhere in main memory, right? In a database management system, it goes to a frame in your buffer. And the black, the solid, or you call it solid rectangular box, that denotes a frame that's occupied, that's holding a page of data from disk. The white frame means that it's a free frame. That means the space there hasn't been occupied yet, and you can use that for additional page that you're going to read from hard drive. Okay? So that's the basic idea of buffer. And the way that database management system manage this is to use this particular data structure, which is very simple actually. You have a frame number, a page ID, a pin count, and a dirty flag. The frame number tells you, basically gives you an index into these frames in a buffer. That's very simple. Page ID tells you if a frame is occupied, which particular page from disk that this frame is holding data for. And the pin count is a number to indicate how many concurrent threads or process are accessing the page on this particular frame. Okay? So let me try to repeat this pin count again, because this is one of the critical parameters in order to understand how buffer works. So whenever a thread requests a page from hard disk, what happens is you look up this page from buffer first. If it's already there in the buffer, you return it from the buffer immediately without going to the disk. If it's not in the buffer, you will send a request to the disk space manager, and disk space manager will translate the page ID into location, physical location on hard drive. Move the arm, do the rotation, do the transfer, and all that, and get that page of data back to you. Then you place that into your buffer, while the frame in the buffer. And at the end of that process, you increase the pin count by 1 to indicate that this buffer frame is currently used by a thread. Whenever that thread is done accessing that page in the buffer, it will come back and decrement the pin count by 1. Do you follow me? Okay? So it's possible that before that happens, another thread come in and ask for the same page. That's definitely possible. For example, there's one person issuing a query, I want to find all CS students. And then in that query, Charlie will be returned on a page. And another administrator comes in, I want to find all the male students of the university, and Charlie will be accessed again. That page will be accessed again. So the pin count for this page will be 2 instead of 1. Do you follow me? The difference is the first process will have to retrieve the page from disk, wait for it to be loaded to the frame, so it will be slower in terms of accessing this particular data. But the second thread get the benefit of the first thread for the fact that some of the data is looking for is already in the memory, in the buffer frame. So the buffer, whenever buffer sees that, it can return immediately and simply increase the pin count by 1. But at some later time, both threads will finish and they will come back and decrement the pin count by 1. So the pin count will go down from 2 to 1, then from 1 down to 0 again. So why pin count is so critical? Because this goes back to what I said earlier about what is system. System is efficient and safe usage of your limited system resources. And buffer is a perfect example of that, because your buffer frames are limited. You do not have unlimited number of buffer frames, because you do not have unlimited memory space. So the number of buffer frames you have are limited, which means at some point you're gonna run out of your buffer frames. So all of this box will be solid at some point. So a subsequent request for a new page, for an existing page, that's okay, because you just return the copy of that page from the buffer. But a subsequent request for a new page that's not already in the buffer will result in problem, because you go fetch that page from disk, come back, try to find a place to hold it in main memory, in your buffer, you find out that you don't have space anymore. You run out of space. And what do? You do something called buffer replacement. Do buffer replacement, which is essentially what's described by this particular algorithm here. So think about what kind of buffer frames you can replace. If you understand what I said earlier about the pin count, it should be fairly straightforward for you to figure out what kind of buffer frame you can actually replace. You can only replace those buffer frames with pin count equal to 0, because if pin count is not 0, that actually means there are some threads are actively accessing that page still. You cannot kick it out, because they may come back and read the data or update the data on that page. You cannot kick them out from the buffer. But for those page frames where pin count is 0, it's definitely safe for you to replace them, because that means there are no active threads asking for the page. You follow me? Okay, so that's how I understand pin count. Question?
What if you don't have a page which is unpaired right now?
That's a good question. What happens if you do not have, you run out of all your frames, you do not have any frame with pin count equal to 0, right? Then you have two choices. Either keep that thread wait, you just keep waiting until somebody come back and decrement another frame, the pin count of another frame down to 0. Then you can finally do the replacement, or you can abort that thread. And I use the word thread because we haven't talked about transaction in database. The right word to use actually is transaction, because every action in a database system is encapsulated in a transaction that has atomicity, durability, and all those nice properties that we have not discussed yet. So I use a thread as a replacement. But later on we will come back to this on how you, because this problem becomes really tricky, because this thread may come from different transactions, and they may have computations between them. And that's tied with the question you were asking. So in respect to that, another choice is to abort some transactions. So instead of waiting, you can tell the transaction you need to abort and try again later. Okay, those are some of the possible choices. Yeah.
So you can also use like a sort of swap space, right? And you can't do that indefinitely.
You mean doing the abort indefinitely, or
like using some swap space on disk?
Well, you can use, yes, you can do that, but that will significantly slow down those threads that try to access those pages. They saw in the buffer, but actually it's from the swap page from disk. That will be significantly slow if you do that.
This buffer is part of database system or is part of operating system?
That's an excellent question. The question was, is the buffer part of the DBMS or part of operating system? The particular buffer we are looking at is inside the DBMS. But in addition to, on top of that, you also have buffer in our operating system. So in practice, it makes it really an interesting problem for a DB administrator, database administrator, to figure out the exact relationship between a buffer in a DBMS and a buffer in an OS. Because sometimes you may find that, okay, my buffer in DBMS is fairly small. However, my performance is still very good. Why is that? That's because you have another layer of buffering at the OS level that cache data for you. So in respect to your question, yes, you might be waiting for a buffer available in the DBMS, but if you do have buffer space available in OS, you can leverage on that. You don't have to wait for space here. However, the next immediate question you may wonder is, if there is already a buffer in place in OS, why you need to worry about building a buffer inside a DBMS? Why do you want to do that? You may wonder that. The reason for that is if you do have a buffer inside DBMS, inside the kernel, then as a database developer, not to develop the database application, but develop the database management system itself, you have control of your buffer space. You can do whatever buffer replacement policy that's in the best interest of your database system, rather than concerning other threads or other applications running at the same time in an OS. So from an OS point of view, database management system is just one of the many threads. So if you give all this control to the OS, you may lose out to some other applications that are concurrently running. Do you understand the argument? So you do need to have another buffer on top of OS buffer. And that's why the very first thing when you set up a database management system, when you install, for example, PostgreSQL, MySQL, or Oracle, they want you to set up how much buffer you want to use in your installation. You may wonder, I never see that when I install MySQL or PostgreSQL. That's because by default, they come with some default configuration. If you, for example, take MySQL as an example, there are 3 default configurations: small, medium, and large. Come with MySQL actually in their configuration folder. Small is for a small server, means limited memory and so on and so forth. Medium is for decent server, and large for supercomputer. And different configuration files, if you check against their configuration files, you can see they set different buffer size, the default value for buffer size differently for those different cases. Yes, you have a question?
What is the procedure to mark a page, page?
Oh, that's the thing I haven't talked about yet. I will talk about that next. Okay, so speaking of update, that comes to the final bit in a frame data structure, which is a single bit called dirty. That's either 0 or 1. Either 0 or 1. Initially, a dirty bit is always 0 for any given frame. It will become dirty, or in other words, it will be set to 1 if there is a thread accessing that page and has made an update to that page. Then that page becomes dirty naturally. Because why is dirty? Because the content of this page now will be different from the content of the same page on hard drive. And this has implication on buffer replacement as well, because now if you do replacement on a page, on a buffer frame that's dirty, you cannot simply kick it out and place a new page into its space. What you have to do is to make sure the content of this page is written back to the hard drive first before you have done the replacement, to make sure that the update is permanently reflected on the hard drive. Okay? So that's essentially what's going on here. The final piece of the puzzle, if you think about this whole thing, is that I may still have multiple what we call unpinned pages. Unpinned pages are those pages, those page frames with pin count equal to 0. I may have multiple of them, and then I need to make a choice. And that's where buffer replacement policy comes into the picture. Different buffer replacement policy will determine which page to be replaced when you have multiple of them with pin count equal to 0. Okay? Some of the popular choices are, that's what we're going to talk about next, buffer replacement policy. Some of the popular choices are, you might have heard of it, you must have heard of these names before, right? Either from online forum or from your OS classes. Some of the most popular ones are most recent use, least frequently used, most frequently used, and some other like clock, so on and so forth. So what are the differences between these different buffer replacement policies? Well, first of all, one thing I need to highlight is all of this are some kind of heuristic, because the performance of a particular buffer replacement policy depends not only on the design of your algorithm, it also depends on the sequence of requests coming in to your system. This is one example where the cost of your algorithm depends very much on the data, the input you have. Some of the algorithms are not like that. For example, if you do a barbell sort, no matter what the input looks like, you're gonna spend exactly roughly n squared time, because you do need to check. You may be able to save some of the swap operation depending on your data distribution, but you have to do this check one by one, right? But buffer replacement policy is where input has a dramatic impact on the cost of your algorithm. Let's look at one particular example. Let's say we look at RRU, least recent use. The name the name clearly indicates what this algorithm does, right? If you have multiple choices to replace the one that is least recently accessed by any thread. So you maintain a timer kind of for each buffer frame you have in your buffer, and the timer records when it is the last time this buffer frame has been accessed by any thread. Then when I come to a buffer replacement decision, when I have to make a decision like that, among the unpinned pages, I choose the one that least recently used. The other ones are, once you understand this, the others are fairly easy to understand well, right? Most recent use, least frequently used, most frequently used. You may argue, you may wonder, okay, among these many policies, which one works the best in practice? The answer is none of them wins out in all cases. It really depends. And this is a subject of very rich research. Let me briefly expand on this. So let's take RRU as an example. It leverages on this particular intuition that if this page of data hasn't been accessed for a long time, then the chance of this page being accessed in immediate future is very low. We know that how to look at this. It's kind of like if you go to any store, right? If this particular item is very unpopular, it cannot be that it suddenly become popular next day, right? It's very unlikely. So that's essentially the same intuition we are trying to leverage here. However, if you try to be an adversary in this particular case, right? If you try to play the role of adversary, you can construct a sequence that RRU will perform the worst. For example, if you have 4 buffer frames and you have five pages on disk, and your sequence of requests is 1, 2, 3, 4, 5, like that. So when you ask for 1, you bring to the buffer. Let's assume we're doing read-only access. That means the peak count of this goes to 1 and then goes back to 0 quickly. Become 1, then it's down to 0 quickly because I'm done with it. 2, 3, 4. These are simple, right? Because when you ask for 1, 2, 3, 4, you have at least one buffer frame that's available, you use that. And we're doing read only, so there's no dirty bit involved whatsoever. So it's a fairly simple case. Now, if I ask for 5, given RRU, what should I replace? I should replace this guy. Because 1 is the least recent used page currently in my buffer, so I will replace this. But if I'm doing this sequential request, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, let's play a little bit more. Next, I request for 1. 1 has too bad. You just replace 1. That's what I want. Fine, I replace the next one. Given RRU, which one I replace? You see how this plays when you are doing exactly the worst case. You are replacing always the next one that you are requesting for. So every single request results in a visit to the hardware. What would be a good replacement policy in this case? If you know, it's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Well, instead of using RRU, you should use MRU. So when 5 comes in, you replace not 1, but you replace 4. Now when you do 1, 2, 3, these are served in instant without going back to disk. You follow me? Okay? So you may wonder, okay, isn't that suggesting MRU is the best? Well, if I'm the adversary, I can do, if you tell me, okay, you switch to MRU. Okay, fine, I do 1, 2, 3, 4, 5, 5, 4, 3, 2, 1. Then suddenly RRU becomes the best. The bottom line is, no matter what you are doing, I can observe what you are doing. And that's the tricky part of the game. I can observe what you are doing and change my request sequence accordingly so that your algorithm perform really bad. So the same thing, of course, we need to formally prove this, but it has been proved before that for any buffer replacement policy, it's impossible for you to design what's so-called optimal algorithm that works for all possible cases. But you may still want to quantify the behavior of a replacement policy, and that's something called, over around 1 minute, and I'll let you guys go. That's something called online algorithm. And to analyze the behavior of online algorithm, you use something called competitive ratio. The competitive ratio is the cost of your algorithm over any input, over any possible input. And you take the worst case of that, the most expensive cost of that, on any input, divide by the same input running on offline optimal. Offline optimal meaning that you can see the future. You know the future and you figure out what's the best thing to do. And for every input you do this, you use your online algorithm, you figure out cost, and you figure out the cost of the best offline optimal. Note that for different input, your offline optimal might behave differently. Okay, that's why it's called offline optimal. You divide them, that gives you a ratio. Obviously, your online algorithm, the cost will always be higher than offline optimal because the best is, that's the best you can do if you know the future. So the ratio, the minimum value is 1. You compare all the cases, right? And you analyze the ratio between these two, your online algorithm and offline algorithm, and over all possible inputs. And this ratio will quantify how good your algorithm is, or how bad your algorithm is. And the conclusion is, for a size k buffer, for most of this algorithm we talk about, their competitive ratio is log k. All of this, guys. Pretty much their competitive ratio is log k for a size k buffer. Okay, with that, I stop today's lecture. We continue on Thursday.